we've gone through ionic and covalent bonding, we need to talk about the polarity of covalent bonds. So we talked about how atoms would share a pair of electrons to make a covalent bond. So say like a hydrogen. Let's use black here actually. Say a hydrogen and a chlorine. They both have single electrons. You can connect the dots to make a bond, right? And we even talked about how that bond was actually a shared pair of electrons that are orbiting both atoms, right, to tether those two atoms together. So I'm sharing here, but that doesn't mean that I'm always going to share equally, right? So I have two electrons in this orbit around these two atoms, but at any given time, those two electrons can be on the same side, right? Whether it be around the chlorine or be around the hydrogen. So when they do end up on one side versus the other, that actually ends up giving you a partial charge, right? So right now the chlorine has both of those electrons in that shared pair around it. That chlorine is going to end up with a partially negative charge. Whereas in the next instant, those two electrons will move back over to the other side around the hydrogen, and the hydrogen will have a partially negative charge, right? But it turns out that some elements are actually better at pulling on electrons than others, right? Which actually can be reasonable to explain. In this case, chlorine is much better at pulling electrons than hydrogen, but chlorine also has much more protons, many more protons than hydrogen does to actually pull on those electrons. So it depends on the case, but in this case, chlorine does tend to pull electrons better than the hydrogen. So we talk about how it has a partially, it's going to have a partial negative charge. Now, when I draw that partial symbol, it's kind of hard for me to do it on this board especially, but it's kind of like a D with a tail on it. It actually kind of looks like a music note to a certain extent, but that just means partial, meaning it's not always charged. I don't have a chloride ion, because that'd be a whole different thing. Then I'd have an ionic compound here instead of a covalent compound. So at least part of the time it's negative, right? The other part of the time the hydrogen's negative, but most of the time the chlorine's going to end up being negative because it pulls on electrons better than the hydrogen does. So if it's partially negative, this hydrogen over here is partially positive. So if I clean this up a little bit, if I have a bond between hydrogen and chlorine, right, there's a separation in charge here, and that's what we call a dipole. Now you can use those positive and negative, partial positive, partial negative labels. I usually use a different symbol, so you need to know what that would look like. Usually I draw an arrow pointed towards the side that's negative, and I'll just put a cross on that other side because that's where the positive is. So you can actually choose either or, right? So don't do them both. It doesn't actually make sense to do both of them all the time. But you can choose to use these labels over here, that partial positive, partial negative, or you can draw that arrow that represents the same thing. So this molecule that I have now does have a dipole. That's that definition at the bottom. Make sure you fill in your blanks. But essentially, that just means it has two poles, one positive, one negative. Dipole literally means two poles. So I can have these polar covalent bonds, right? If I had, right, any given bond, let's think about one that we've talked about before, right? That bond between an oxygen and a hydrogen in water. We should know from prior experience, especially in biology when I talked about it, that water is a very polar molecule, right? And the oxygens pull much, much harder on electrons than the hydrogens do, right? So when I draw symbols like this, I'm showing that there are polar covalent bonds in that molecule, and there are dipoles, right? I have two distinct regions here, one that's partially negative, right, by the oxygen, and then partially positive by the hydrogen. Again, I'm doing this for emphasis right now. Usually I wouldn't actually use both symbols at the same time. I'd only use one or the other, right? So either use those partial negative, partial positives, or draw your arrows. Otherwise, nonpolar covalent bonds exist when atoms pretty much share those electrons equally. So in the case between a carbon and a hydrogen, carbon isn't actually all that much better than hydrogen at pulling electrons. So you don't end up having that separation in charge, right? In that case, it's going to be a nonpolar covalent bond. And then you're just going to draw that bond the way you draw any other bond. You don't need any special marks, right? If I had a methane molecule that we'll talk about later, and we'll even talk about the shape of this thing later, right? All four bonds to hydrogens in here are going to be nonpolar bonds, and this is going to be a nonpolar molecule, right? We'll talk about the actual molecules themselves and their polarity later, but for now we just need to be able to identify bonds, what kind of bonds are polar and what kind of bonds are nonpolar. So actually you're going to use technically some information out of a book that you never opened, so we're not even going to worry about that. I mean, if you do ever happen to reference to that book, this is necessary, but otherwise we can probably just cross it out. We're not going to use it right now. But we are going to use an electronegativity chart. And electronegativity is actually that tendency to attract electrons I was talking about a little bit ago. So when chlorine was better at pulling electrons than hydrogen, that means that chlorine is more electronegative than hydrogen is. It's better at pulling electrons. It has a higher electronegativity. And we're going to use these boundaries from the book, right? But you don't need the book. We can just write them in right here. We're going to use these ideas, these guidelines, right? I'm going to have separation and electronegativity. And if that separation is less than or equal to 0.4, I'm going to assume that that is a nonpolar bond. If it's greater than 0.4, it's going to be a polar bond, right? There are also ionic bonds, but I don't really use boundaries to identify ionic bonds because that's actually more misleading than helpful. So I don't use that. What I do to identify if it's an ionic bond is I just look at it, right? If I see a metal, it's automatically ionic, right? The only way it can be a covalent bond, period, is if you have two nonmetals. So you can have nonpolar covalent bonds, you can have polar covalent bonds, but ionic bonds are between metals and nonmetals. So if you see a metal, it's automatically ionic. So again, I need an electronegativity chart for this. Your sub should have handed out one of these electronegativity charts for you. But basically, all these numbers on this periodic table are just telling me how good that element is at pulling electrons. So if you look on the right side and top of this chart, nitrogen, oxygen, and fluorine are better than any other element at pulling electrons, right? They're really, really good at it. So they have high numbers, 3.1, 3.5, 4.1. Whereas down and to the left, when you look at like, say, potassium, rubidium, cesium, right, those kinds of elements, they have really low electronegativities. But that makes sense because metals don't like to keep electrons. They want to lose their valence electrons. So they don't hold on to them very well, right? So what I'm going to do with this chart is with examples, say like my oxygen, oxygen to a hydrogen. If I didn't already know that that was polar, I could look at the chart and I could see that oxygen has a 3.5 and hydrogen has a 2.1, and I would just subtract those two values. And when I do that, I get this 1.4, and from that previous list, 1.4 is much bigger than 0.4. So that is definitely going to be a polar bond, right? The only thing from there that I have to understand is the thing that's more electronegative is the thing that ends up negative, right? So I need to point this arrow towards the oxygen if I'm going to identify a dipole. So first thing I wanted to know is this polar or nonpolar? This is definitely polar, but I don't usually have to write that it's polar. I can indicate that it's polar with a dipole, right? So when I put that arrow in there to represent which thing's negative, which thing's positive, that actually tells me that it's polar. So you don't actually have to tell me that it's polar, right? Whereas again, just a second ago, we talked about a carbon and a hydrogen. Carbon is 2.5, hydrogen's 2.1 on this list. So if I take 2.5 and I subtract 2.1, and yes, I'm aware you can do that in your head, but I'm just showing you because I can. So that 0.4 is exactly that value we've been looking at, right? If it's less than or equal to 0.4, then it's going to be nonpolar. There are actually some chemistry books that would consider this a polar bond, but for our purposes, because all organic molecules that we talk about later that only have carbons and hydrogens in them are going to be nonpolar, we don't want to think about this as being a polar bond. It'll just be confusing for us. So this is a nonpolar bond, right? I do actually have to say nonpolar this time because I'm not indicating a dipole. If you didn't say something, I would just assume you didn't do this question, right? So if I was asking you, are these bonds polar, nonpolar, ionic? If you show me a dipole, I know it's polar. If you say it's nonpolar, then I know it's nonpolar. But otherwise, you do have that last option. If I had, say, a magnesium and a carbon, it doesn't matter what my elements are. If I look them up and I see magnesium and I see carbon and I'm like, oh wait, magnesium's a metal, right? As soon as you know that magnesium is a metal, you're actually supposed to be able to identify this thing as an ionic compound, right? That actually wouldn't be a covalent bond, right? Instead, you'd likely have that positive and negative charge for those things and that attraction between those two ions, right? So I will give you those as options, and you're supposed to identify that those are actually ionic, they're not covalent bonds, right? But otherwise, you don't have to do the positive negative. You don't have to show that it's an ionic bond other than to put an I next to it so I know that you thought it was ionic. Otherwise, right, you just can go ahead and do other examples. I can do a couple more here real quick just so we can see what it might look like. So say I had a nitrogen and an oxygen and maybe a hydrogen, oops, pen's going goofy again, and a fluorine, right? When I look those things up, right, nitrogen, oxygen, 3.1, 3.5, when I subtract those things, it's actually a 0.4. This would be a nonpolar bond. So I would indicate that it's nonpolar. I just write NP next to it. Otherwise, hydrogen and fluorine, again, I'd look it up. Fluorine's 4.1, hydrogen's 2.1. That's a separation of 2. That's huge. That's way bigger than 0.4. So I know that this is polar, but I also know that the fluorine is more electronegative than the hydrogen. So I'm going to point my arrow to the right. So when you do a dipole, make sure you're always careful because you point it in the direction of the bigger number from our electronegativity chart. Fluorine is to the right in this molecule, so I pointed my arrow to the right. Up here, the oxygen in my oxygen to hydrogen bond was more electronegative, so I pointed my arrow to the left. So always point it in the appropriate direction. Otherwise, you guys should be able to finish that octet rule worksheet, right? Doing everything on there. And that's it for notes today.